Today we're dealing with conservation of momentum, which is very much like conservation of energy. So when we were dealing with conservation of energy, we basically took into account like two different positions, and we said that the total energy at this spot is equal to the total energy at this spot. When we talk about conservation momentum, what we're saying is that the total momentum before is equal to the total momentum after an interaction. Okay, so we have two things kind of interacting with each other, or one thing becoming two different things. So the types of interactions that we're talking about are collisions, where two things crash into each other, and explosions, where you have one thing and it becomes two things. So an example of each would be, so a collision would be, just like its name implies, an object running into another object. Okay, so two people running into each other, two cars running into each other, one car running into a parked car, those would be all collisions. But an explosion could be like our traditional, what we think of as an explosion, where we have a bomb that is breaking up into two parts, and so you have it stationary to begin with, and then you see that it's gonna move, and each part's gonna move off into the other directions. Or an explosion could be like two figures that are starting together and they push off from each other, and each figure ends up going in an opposite direction. Notice that Newton's third law still applies. I push you, you push me, and those forces are equal and opposite. That's actually going to be an important idea to keep in mind, is that those forces are equal and opposite. So just like with conservation of energy, we found the total momentum at one spot and the total energy at one spot, total energy at another spot. What we're going to do is the same thing, and it's before the interaction, so like before the two cars collided, or before the two skaters pushed off, or before the bomb exploded, equals the total momentum after, so like after they do their interaction. And again, the force is the same for both. I'm going to actually write that. The force on each object is the same. And that's Newton's third law. I push you, you push me. Okay, so let's look. We're going to do two problems. We're going to do one where they collide, and we're going to do one where they explode. So here's a sample. 5-year-old Joy, whose mass is 20 kilograms, is running at 3 meters per second to greet her 55-kilogram mommy, who's standing still on roller skates. How fast will Joy and her mommy go after she catches her? So let's draw a picture. Here's little Joy. Okay, and she is 20 kilograms, and she's running at 3 meters per second. And she is going to greet her mommy, who's standing on roller skates, and she's stationary. So 55 kilograms is mommy, and she's stationary, so she's going 0 meters per second. So this is before the collision, and that has to equal after the collision. Okay, so after the collision, mommy on her roller skates is now holding Joy, who has jumped up to her. So afterwards, the total mass is both their masses together, okay, because they're moving together. So we're going to add those masses together. So this is 75 kilograms, and we want to know what is their velocity after. We don't know that. So see how a picture kind of is worth 1,000 words? We have before and we have after. And we know that the total momentum before, so when we add these two guys together beforehand, is going to equal the total momentum afterwards. So let's make this a little bit smaller so we can have room to work it out. So we know that our total momentum before has to equal our total momentum after. So the momentum before, we have Joy, who's running. She's, okay, momentum MV, and MV of Joy plus MV of Mom has to equal the MV of them together. Now, because they're stuck to each other, they're going to have the same final velocity. That's known as an inelastic collision, which we are going to get to next. So we'll differentiate between inelastic and elastic collisions. So the MV before, so the mass of Joy is 20 kilograms, and she's running at 3 meters per second, plus the mass of Mommy, who's not moving, so she has a velocity of 0. So actually this term will go away. Equals the mass together, so 75 V. Okay, so after the collision, solving for V, we're going to get 0.8 meters per second. Now, since this momentum is a vector quantity, by the way. So since this momentum was in this direction, this final momentum is also going to be in this direction. So they're going to go 8 meters per second in that direction. They're not always going to, in an inelastic collision, they'll go in the direction of whoever's got the larger momentum. We'll get into that later. Okay, an explosion, same idea. Okay, so now we have Joy and Mommy on skates. Here's Joy, and here's her Mommy. And they're on skates, and they're going to push off from each other. So initially, let's move them over. Whoa, didn't want to do that. Okay. Initially, they're going to be together, but then Joy is going to go off in that direction. She's on skates. Everybody's on skates. Why are we on skates? Because then we don't have to worry about friction quite so much. If we were on ice skates, it's even perfecter. And then Mommy is going to go back the other direction. Okay, so before, Joy was 20 kilograms, Mommy was 55 kilograms, and they were stationary. And then they pushed off. We're gonna have to know the velocity of one of them, or we could actually know the force and the time that it took them to do that, but we'll just give you a velocity. So let's say Joy ended up going off to the left at 3 meters per second. And we want to know how fast is Mommy going in the opposite direction. Okay? So this is before, and this is after. So the total momentum before is 0, because 20 times 0 is 0, 55 times 0 is 0, so total momentum before is 0. Now remember, this is vectors, so Joy's velocity is off to the left, right? So, correct. So she's going to have a -3, so 20 kilograms times -3 meters per second, her mass times her velocity, added to the mass velocity of mommy. We're trying to find mommy's v. Okay, and when we solve for that, we end up with a positive 1.09 meters per second. So we also know that they went in opposite directions because mommy's velocity came out to be positive when we did it. So remember, positive, negative in physics tells you direction. All right, so that'll get you started. And then we'll have inelastic, elastic collisions, and then we'll have 2D collisions, so where we have to go up and over.